insane pleasure to introduce the next speaker, Sophie Mercier, and we've known each other 30 years, I think, maybe.
That would make me very young.
Well,
Like 5 or something?
You were, well, yes. Sophie is a professional engineer, building enclosure expert, building envelope expert from Vancouver, British Columbia. And Vancouver was perhaps the center of interesting issues 20 years ago when you were a teenager with the condominium crisis. And we learned a great deal, and it would be nice for Sophie to, you know, she's also founded Evoke Corporation. She's the founding partner of that. And it would be nice to maybe talk about the lessons that we should have learned and what we should be doing that maybe we didn't do or whatever. So with that, please welcome Sophie Mercier.
Okay, I think I'm gonna start with a confession. Joe reached out, he asked me to come and present and call them, talked a little bit. Of course, I was extremely honored. I was also very anxious of doing a presentation in front of 500 people that know really much what they're talking about. So I kind of went to bed and I started thinking about what is it that I'm going to talk about exactly. And I put something together the next morning or so, sent it off to Joe, and everything is good. I didn't think about it too much until the updated agenda came out. And then I look at the website and I download the agenda and I read what I sent you. And I'm like, what hell? Like, what did I set myself up for? This is what I want to hear. It's not what I have to say. Anyway, I'm gonna try my best today to go over some stuff. And while the leaky condo crisis is gonna be part of it, it's gonna go beyond that. Because part of it, I think, is the fact that, yes, I started a new firm 5 years ago. And what does that mean when you start something new and you don't have access to the files that you've been using for 30 years, right? You don't have a lot of photos, you don't have a lot of those things, but what you have is what you've learned. So I'm gonna try to go through some of those things today. So I said I was 35, right? Don't we all want to be 35? What is nice about that is that I have some friends that remind me what age I am. So every milestone birthday that I've gone through, I received a cake. Well, maybe not every, but the last 2. A few years back, I got this one. Good. And just a few years ago, this one. So, jokes aside, an experience that stuck with me a little bit more recently and why this talk kind of resonated with me is that I went to a mentorship. It was like speed mentorships. Like you sit at a table, there's 8 people, they ask you a bunch of questions, they have a certain amount of time, they move on to the next one, right? As part of the introduction, they asked me, you know, how did you come about doing what you do? Because that's what the speed mentorship was about. So I explained that when I came to Vancouver, I had no clue about building science. I didn't even know it was a field you could practice in. But there was something happening in Vancouver that was called the leaky condo crisis. And that's what got me into it, right? So I explained a little bit how that went about, finished my thing, and people come up to me and it's like, the leaky condo crisis, I read about that. That's when you know you're a bit older because you're part of the history book as opposed to having lived through it, right? So like it's a different thing, I guess, realizing that your experience matter and you need to talk about it. So I think that because my focus professionally is a bit more narrow, and I come from a place that's kind of a little bit far and to the north, it's important to kind of say who I am professionally. Joe said I work on the enclosure side. I have about 27 years experience, 22 of which were with Morrison Hershfield. I started from the ground, like I didn't know what building science was before I started, but I had good mentors. One of them was Mark Lawton. I worked beside him for like 22 years, so I learned a lot from him. I managed people also. So I worked in offices from Edmonton all the way to San Francisco. I had a glimpse of what was happening in other places, but my technical stuff all happened in Vancouver. So I think that it's important because as I'm talking, I want you to realize that I'm talking in the perspective of what I've worked in and some of the things that I've taken out of it. Mostly the type of building that I've worked on were larger, non-combustible buildings. So very few houses, but rather like steel stud concrete and quite a bit of residential. And I'm gonna try to keep it to that, not go into the commercial side or the institutional side. And yeah, 5 years ago, started a new practice and been working on a little bit more the technical side, thankfully, that realizing that when you get back to the basics and you need to deliver the jobs and you roll your sleeve and you really go into it, and a little bit more mentorship as well. So Vancouver, zone 4, lots of rain, not tons at the same time, but it rains from November to April nonstop, right? So we deal with not like snow or things like that, but a lot of rain. So I mentioned Mark, one of my mentors. Another guy that was in the office for the 22 years that I was there was Pierre Gallant. And he was more on the office side. He knew what he was doing, of course, but he was kind of like the guy with all the sayings. So there's a lot of stuff that he said that have stuck with me, and there's a bit of mix between those two here. But some of them, of course, don't have all to do with building science. The first one is hire for attitude, you can teach the rest. I'm the living proof that Pierre was living by this saying. Because he hired me, I didn't know squat, and I had a lot of attitude. So the second is you can make a mistake, but don't make it again.
Yeah.
Right? Who doesn't learn from their mistake? That's what you remember. You get burned, and like you will go to great extent not to have it repeat itself. I would add to that, you can make a mistake, but don't make it again. And if you make that mistake, make it small. Don't do it on a super large building where there's thousands of the same detail, right? Right. So test on small stuff. We're both advisors and gatekeepers. In my profession, I work truly, like I might be hired by a developer, but I work truly for the architect. Side by side, advising them of what can be done, trying to, through my advices, to guide them into something that will work better. Ultimately, they are the designer, right? But there's a point in time where things can go too far, and that's where the gate should come down. So that's one other lesson that I was told and learned and still rings true today. Another one is, it doesn't matter so much what you know, it's how you communicate it. And that's something that I've worked on all my career. At the beginning, like the arguments that we would have to realize that we were saying exactly the same things, like it happens all the time. It still happens today. But communicating is so important. We have to put effort into that. But something that's a little bit more relevant to today's presentation would be, we've done that before. That's Mark Lutton. Every time someone young and excited would come up to him and say, we should test this and we should do that, and like, it's been done. Just read about it. Just go ahead and like learn from what other people have done. Doesn't mean that it needs to stop there, but there's a lot of things that have been done, not necessarily just in your little circle geographically, but elsewhere, that we can learn and build from. So that brings me to the first thing I want to talk about, the drainage cavity. I think that we were, it was about 2 days ago, I was talking with Joe and someone came and started talking to us, and he asked Joe, like, if I'm new to building science and I want to learn, like, what do I do? Like, where do I go to learn those things? And you said 2 things. It's like, first of all, read the Building Science and Science, the 150 of them, right? And the second is like, go to the CBDs, like the Construction Building Digest. So it's fitting that I had one in my slides already. But coming back to the cavity, it's not something that is new, right? Like, it's been written into articles a long time ago. Well, long time ago, 1963, this publication, and there was others around the same period that talked about that. What's interesting is, like, I took that snapshot, is like, they're like, the problem is virtually eliminated. So, like, if everybody had read this thing, we would think that we wouldn't have had a problem in Vancouver, right? This is an extract. They're not very long either, right? They're like 8 pages. They're very easily read, and you can digest them very easily. That's just what I thought was a good summary of it. As with capillary suction and gravity, water entry resulting from an air pressure differential can be controlled by the introduction of an airspace in the joint or wall, right? What a simple approach to designing one. What's interesting about that singular one is that it's missing a critical component. And funny enough, when I Googled it, I didn't find the CBD. I found John Straub's commentary on the CBD, and I thought that it was quite fitting. What he says is that while much of the article remains correct and relevant, the most jarring omission in the document is any mention of what today is fundamental to the concept of drain-rain penetration control strategies, and that's the drainage plane. And perhaps if you ask Joe, it will tell you where that word comes from. So after the publication of the CBD, we had the adoption of the cavity in Canada. Some people did read it, but eventually people forgot. And in the 80s and the beginning of the 90s, like, it disappeared almost completely in Vancouver. As a young engineer, like, fixing leaky condo with face seal cladding, I was quite impressed one day when I had to do an investigation of a building that was built in the early 70s. And it was not because it was leaking, it was because it was like those little square tiles. And it was a high-rise, and the tiles were falling off, and we wanted to know how it was built so that we could design something to replace them instead of just trying to glue them back. And opened the wall, and there's a cavity behind it in 1970. That's when I learned about the CBD, because I came back to the office and I was like, oh my God, look at this, they had it. Mark said, yeah, read that. So, yeah, so there was cavities in facade before that, but then people forgot. And that brought on a big mess. Like, the leaky condo crisis, mentioned it a couple of times. it culminated into a commission of inquiry that looked into the quality of construction in BC that got published in '98. At the same time, the codes were changing to try to adapt, and the building envelope professional became a thing. I don't know if you guys understand a little bit the market in Vancouver when it comes to professionals, but on new construction in the Lower Mainland, which would be Vancouver and the cities around it, when you build a project of scale, you need to hire a building envelope professional. So as an architect, you could do it, but most of the time you end up with hiring someone like me who needs to sign schedules for moisture, air, and rain penetration, air, and vapor. So how big was the problem that we faced? Again, I don't have a lot of data from that time, but Dave Rickett did a really nice presentation at BC Beck, and I stole the newspaper from him. In BC alone, $4 billion worth of repair because of leaks. And that affected more than 30,000 units. That's a lot. And some of the things that came out of that, I mean, how long did it take to repair all that? I think that there's some buildings that are still not repaired today. Some people have been putting their head in the sand for years, and some are being fixed by court order. Like when the owners cannot agree to repair their building and get a vote that can pass a resolution to do it, the courts eventually step in because buildings are shored up and the structural components are kind of getting to nothing. That reminds me of another story. It's like you go to site to repair some of those things. Have you guys heard of structural stucco?
Like structural paint?
About the same, I would say. But the first time I'm looking at things, I'm like, they're starting to take the stuff on the ground floor, and I'm on the second floor, and I go to look at something on the balcony. The guy's like, you should step back. I'm like, okay. I get out, I go down below. They had removed the stucco on the column. There was dust in the bottom. That's all. No wood left. Zero. So, structural stucco. So the other thing is that, I'm talking about it in my perspective, right? I was in Vancouver. That's where I saw the thing happen. But there was similar stuff, perhaps not on the same scale, perhaps on the same scale, that happened everywhere, in other places, with a bit different climate zones as well, perhaps at a smaller kind of time frame, or a longer time frame to get the deterioration there. But there's places like New Zealand that we hear still today that they're dealing with that kind of stuff, right? So anybody that experienced it up close, or even people from the outside looking at it, everybody had their kind of reason why it happened, right? This was this, and it was because of that. The reality of it at the end of the day is that there was many contributing factors. Like in everything, there's always many causes, some of which are more important than others, but it comes from all sides. The ones that I put here are from the Barrett report. So I didn't try to make it up, but the design features were inappropriate for the climate. And what was happening in Vancouver at the time was that postmodern, I guess, and trying to imitate California style, and removing eaves, and using new material. Before that, there was a lot of wood siding and so on and so forth. By that time, stucco became really the thing of the day and starting using that at big scale. And on top of that, there was a reliance on face seal wall assemblies. The funny thing is, like, what I'm going to talk about hasn't changed very much. We have the same pressures today. But in Vancouver, real estate is very expensive. So people build to the maximum size they can. And like, if you can eliminate even the 3/4 inch and give it to the suite that you sell, it's worth it. So that was a problem too. That put pressure and make the use of face seal system a thing. There was a fundamental lack of awareness regarding the principles of enclosure design suitable for a climate. And the suitable for a climate is the important part as well, right? It was 1986, there was Expo, and there was a huge boom in construction after that in Vancouver. So like, there was a lot of construction and not enough people to build, and the experience of like the trades was not up to snuff because a lot of new people came in to try to build things, sometimes from other places. So here we were with like a lot of people that didn't have the fundamental knowledge to build something that was working for the climate. There was also a lack of meaningful inspection at critical stages of the construction. In fact, I think, 1993, up until 1993, architects and engineers were not required to certify that the design met the requirement of the building code or their drawings on site. So, yeah, big thing. And of course, even though they were seeing that failures were happening, the municipalities, the authority having jurisdiction, they were not able to react to change the way they were doing things. So that mix was a bit toxic and ended up having the effect that it did. So that was kind of my first point. Like, I'm not just gonna talk about the drainage cavity, but I want to round that one up with, is history repeating itself? Because what I'm experiencing at my end in Vancouver right now is that up till now, perhaps we are gonna have some breathing room finally, but not for the good reason, is that there's been a boom in construction. Everybody's like, we need to build more, we need to build more. We don't have all the trades like that are equipped with building things like we want it to be built. In fact, like, I've been going to site for like over 25 years, and I'm always so surprised that a trade doesn't understand how to do a subsill flashing, like how to kind of like deal with a saddle properly, right? And I think that more than ever, like, I don't know if it's movement of people between companies and that kind of stuff, especially at the trade side, but also within our industry, is that mentorship is not the same as it used to be. I had the privilege of working with one great person for 22 years. Not a lot of people have that opportunity anymore when they move and move and move, right? You don't create that kind of condition. And because of cost of things, V is like the pressure of the day. I don't know how many times I'm like sitting at a meeting and the project has been tendered and all of a sudden like we need to do something about it, otherwise it won't get built. And what do you eliminate? And what do you go with? And I don't know about you, but like every project I have a new material on it. Like, it's like a new membrane that I haven't seen before, a new cladding that was never used in BC, a new, like, it's every project that I do. And like I said, like with the footprint of the building, like there's like, everything is pushing in the wrong direction still. The city of Vancouver actually was kind of recognized that a little bit, and they gave exceptions for the drainage cavity. So they say you don't have to count it on your floor ratio. So please go and do it. Like, we won't penalize you for it. So that was a good thing to do. But there are some new formula today that are actually pushing us in the other direction with insulation. So how do you kind of manage all that? Anyway, I don't think I have an answer for that. We need to be aware, and we need to be vigilant all the time. It's not because we've learned something that it won't happen again. But in this case, I'm not questioning the drainage cavity in Vancouver. That's well entrenched now. But those factors that contributed to it are still there. So something else can happen. The second one I wanted to talk about is better insulation. This one, not so much because of a failure, but more in terms of its evolution and how we can build on what we've done before. Just an example of it. For a long time, buildings were built out of stone, right? No insulation whatsoever. Eventually, the frame building came into play, and there was that nice cavity. So by convenience, I guess, and for more comfort, people started putting things in it, like, I don't know, newspaper and whatever you had on end. Eventually, the insulation, because of the oil crisis in particular, kind of picked up in terms of developing better materials suitable for what we need them for, more resistant to moisture, for example, with a better R value, of course. But again, I think that we're working on materials all the time, but there's a little bit more stagnation that happened in the 80s and 90s. There's a kind of something repeating here. 80s and 90s, what were people doing there? The energy cost nothing in the 90s, right? So there was no huge incentive to work on it, I guess. And so up until more recently, where we're starting to take care of insulation, not just by itself, but in the context of an assembly, where we look at its efficiency within the context of the building. So I'm working with one of our partners, Patrick Ropel, and he's kind of the guy behind this. The story that I'm going to tell to kind of demonstrate that you can build on what you've done and get to good places. We were all at MH, at Morrison Hirschfield, and we were working on the Olympic Village. There was quite a few projects being built around the on the village because of the Olympics, so they were all serving to kind of house the athletes. And part of kind of the goals of that development was to be LEED Platinum. And by trying to stretch the goal a little bit further, for a number of projects, and having a lot of the firms that wanted to do the right thing at the table, there was a lot of discussion as to how are we going to achieve that in terms of making the building thermally adequate to meet those targets. At the time, there was very few in Vancouver, very few exterior insulated buildings. At that point, I think we were a city of window wall, 70% window, floor to ceiling with spandrel. So there was not a lot of data out there to help with the program. And what was happening is that we realized very quickly we needed to put insulation outside. We needed to have framed wall with lots of insulation. We could not do those things in window wall. But calculating what was happening, especially with the outside, there was not a lot of data out there. So here you had young Patrick doing 2D modeling, trying to, every time there was a VE, he had to do a new one, and so on and so forth. So after a while, it's enough of that. I'm going to do a big spreadsheet and try to think about everything they're going to kind of asked me so that we can make some good decision-making on the spot as opposed to going back and forth. So the first iteration of that was just a spreadsheet. And there's an extract of that spreadsheet just down there. It's like, it just compared like different type of insulation on the outside and different types of attachment that you could use. And he modeled all that and kind of put it forward, and that was helping making decisions. So it was comparative and very helpful. On the footstep of that, the team at MH wrote a paper, and it helped kind of consolidate, like when you write a paper, you think about things a little bit more even, right? With perspective somewhat. And it came to a point where like there was work there that we needed to push forward. And the first project that was done in trying to develop perhaps a bit more around the methodology on how to do the 3D calculation. When you talk about non-combustible building, it's all very conductive material. So it's a little bit harder to imagine how the heat flows are going, and it's a little bit harder to evaluate properly if you have like things that happen in 3D, more metal here than there, and this and that, intermittent clips, for example. So the ASHRAE 1365 was like the first project that kind of looked at validating the procedure to get there. And of course, we didn't invent it, we borrowed it. We looked at Europe and what methodology they were using there. And in the, kind of like the process of that, our goal was to help raise the awareness of the impact of thermal bridging, right? Like starting understanding better what those impacts were. It was, I think, quite successful, and out of it, there was a lot of discussion to try to produce something that was a little bit more appropriate for practitioners to use, to kind of take on that methodology and apply it across the board. And that required a lot of funding. So gathering funding is a lot of kind of going to people and convincing them it's the right thing to do and all that kind of stuff. So it took some time. In between, what Patrick ended up doing is like, and helping is search for money, for funding to do the next step that he wanted to do, was to produce those kind of solutions where he broke down some of the most kind of asked questions. The clip one was one of them, like, what's the difference between Z-girts on the outside that goes through the insulation? What if you do them crossed instead? Like, what happens if you put them intermittent, right? Like, so that was the first one. The other one, I didn't have a copy of it, unfortunately, was like the spandrel section in curtain wall. What is it worth, truly? Right, in 3D, and how does it scale with the size and so on. So those were two that were quite successful and help actually launch into the thermal bridging guide. So that was the tool that we needed to help everybody get on board with that kind of new methodology for the area. First, it established like exactly how you should be looking at thermal performance of an envelope, like looking at the fact that you can take, like they do in Passive House, the area of the components you're trying to evaluate, like the wall, for example. You take the clear field value, you multiply by the area, you add the linear transmittance, multiply by their length, and the point transmittance multiplied by their number. And you divide everything by the area. It's a very simple calculation if you have all those numbers. So the thermal bridging guide was an attempt to, a first pass anyway, at getting numbers out there. So not only did it describe how you needed to do the methodology, but it modeled a number of details and assemblies, and it put that as an appendix to the technical part of the guide and put it out there. The first edition, 600 pages. Most of them, details. So you see why the funding was important. So, I guess I explained that a little bit, but what I wanted to say about this is that as we went on and you do those things, like it became part of code. Like the guide was so well received that it actually influenced code in the region. And we're lucky in a way because the way the code works in Canada, you have the National Building Code, and then the provinces can either adopt it or kind of modify it slightly. In BC, they modify it slightly. But more than that, the city of Vancouver has its own code. So I think that what was very helpful in this process is that there was a large group of people in Vancouver that wanted to do the right thing, and including at the city. And at a small scale, it was easier to affect changes. And when the province saw that it was working very well, they extended it. They looked at the ramification of other zones, but they extended it and they adopted it at the provincial level. Instead of waiting 3 code cycle at the national level to actually trickle back down. So that was one good thing that came out of how it was structured. There's a whole slew of bad things when everybody can do their own thing, but that one was a good thing. Anyhow, so we do those projects now and we use that all the time. The thermal bridging guide is like the basis of how we need to do calculation to give input to energy modelers that will provide what the building performance is. And what's become evident in doing many, many of those is that the details contribute 30 to 70%. 30 at the kind of, this is a good building, will have about 30% heat loss through the detail. And a building that you didn't pay attention whatsoever to, right, could have upwards of 70. And why do we have 30? And again, that is non-combustible construction, so steel studs, so a lot more conductive than wood, right? Like, I mean, you cannot do without windows, right? So you'll always have some window perimeter, wall to roof transition, base of wall. You will have architectural features regardless of what you do. Another one that became evident is that the window perimeter was often the largest contributor to the heat loss. So of my experience, if I give you 2 things on the non-combustible building, is that pay attention to your window and pay attention to the details, generally speaking. It's not just about the wall selection you make. So I said it was 600 pages, right? That was in 2015. Then it was successful, and people were like, but what about this detail? What about that detail? So there was more funding. We did more details and more detail. Version 2, 3, 4, I don't know how many pages it is now. In fact, it's a bit obsolete because with so many pages, how do you find what you have, right? So the next project that was also funded was to develop an online tool that stored all that. And that is on thermalenvelope.ca. The database of all the details that have been done today to that methodology that was established for the thermal bridging guides are on that website. And they can be searched like by type, You can actually look at also, like if you're targeting a certain performance, you can target that performance and it would give you details that could achieve that. So great resource. And there's other tools on there and training as well. So I invite you to go and have a look. To somewhat wrap up that story, I think that one of the lessons of that is that with better tool, better results. With better results, better tools. And it's a vicious circle that goes to make things better, right? Building on what you've done before, getting to a good place, but we're not done yet. There's tons more to do. The funny story about that is that when Patrick started and he did the first research project and the thermal bridging guide finally was issued, it's like, whew, I don't plan on making that my career. He's still doing it today. So it's important work, and I think that there's still a lot to be done. Another thing that I wanted to kind of talk about is, I guess, charting the path ahead might be what the giveaway I want to give here. As part of the changes of how we were doing things with the energy and buildings in Vancouver, the city of Vancouver, but also the province, they had their goals to 2030 and beyond. They looked at what they needed to do to kind of do better with what they were doing on the carbon side, and they've established that goal. At the time in Vancouver, from a builder's perspective, there was a lot of like pushback on change. Like, I think it's kind of normal human behavior to kind of like being a little bit resistant to too much change. And one of the ways that they try to kind of mitigate the pushback, was to actually chart what the change would be up to 2032. So they said, listen, this is where we want to go. This is the study we've done. We won't ask you to do this from the get-go because we might set ourselves up for failure to have everybody, an entire industry, go and do the top building. So let's chart the path. And the idea was that at first, the step one, it's disappeared now, we're already at step two. Step one was in 2018. The step one was only to report. So because it was a new methodology to go with energy intensity, like we were measuring total energy intensity and thermal energy demand intensity. So because it was a change to do it that way, before that mostly it was like ASHRAE methodology or NECB methodology is the Canadian kind of equivalent of ASHRAE in terms of energy modeling. And like it would be compared to a base building, right? Now they wanted you to report the intensity of building. They also wanted you to trust that the data that they had gathered to establish those targets was actually feasible. And they wanted also to confirm, I think, for themselves that what they had decided was actually going to work. So the first step was to report. And one of the kind of like political contexts in which they pushed that is that most of the municipality around Vancouver would go to developers and ask for different things. So there was a code minimum that they needed to kind of build to, and to gain more density, a couple of stories more than what the zoning said. Well, can you do this for me then? Like, so they would add all those demands on the developers, which were different depending on the municipality. So the province thought, if we put that and we say to the municipality, the only thing we can do is ask for a different step, then at least we kind of like are in line with the same methodology, they will know what to expect, and so on and so forth. What the province didn't think is that the municipalities would go and try to outdo themselves as to how high of a step they would ask. So at the beginning, not everybody, some were not kind of necessarily tapped in and they didn't ask for anything. But a few of them went on and from almost the get-go asked for step 4. And I can say that some of those municipalities since then have actually taken a step back. And just realizing that at the scale of an industry, I mean, I admire what I've heard in terms of presentation, because like you have one building, you can do a client that wants to do the right thing, and you can do those things. At an industry level, is it already 2? No. Okay. At an industry level, you cannot just like expect an entire industry to just jump in and be able to build those things, understand them, let alone engineers kind of supporting the design of those buildings and not just screwing it up in the first opportunity they have, right? So, yeah, like I think that it was good to have that. It was good also to realize that the steps were an important thing. Perhaps they could have been more rapid at the beginning. The thing that is a little bit harder to realize here is like 20, 40, 80, you think like, oh, it's just doubling the efficiency, right? But like that curve of diminishing return on a lot of things that we do becomes really evident between step 3 and step 4. So the incremental effort is much more than double in those 2 steps. Another thing that they introduced more recently, not to introduce everything at once, is the GHGI kind of step code. And they have 4 levels. And at the moment, we're at the measure only, but a lot of municipalities are kind of picking and choosing a little bit. They say, okay, you need to meet step 3, but if you do EL4, which is full electrification, you can go to step 2. So like, which is still permitted, right? So there's a little bit of that kind of give and take that's happening between different municipalities requesting different things, but realizing that and I should be clear, like that is operational carbon, right? So that there's kind of a relationship between the thermal performance of your building, right, and the carbon you're using are both important, and that if you can balance those 2 things, maybe you're in a better place. Okay, so that leaves the question, is net zero really an achievable target for an entire industry? I don't know. And like, I mean, it is a lot of buildings, right? But what I have to offer is this, is that net zero is a lofty goal, yes, but is a necessary goal. Because I think that we always aim for something, and if we could get to at least a good part of it, we would be in a good place. So, like, I think that it's an important one. I hope that we will be able to achieve it. Perhaps not by 2032 is what I'm kind of seeing in the progress of where we're at, but at least at some point in time, soon enough. My third one, whole building airtightness. So the history of air barrier goes back to the 70s, right? And probably was brought on by the oil crisis again. Building professionals were kind of looking for ways to make building more energy efficient. And they quickly realized that if they were able to control the air leakage, it made a difference, a significant difference. So air barriers in Canada became code in '86 and started being installed more kind of like regularly and so on. And up to today, where like now in Vancouver, we are actually, as part of STEP code, required to test the building at the end and report and meet a certain target. I'm gonna read a little bit here, but Canada was certainly at the forefront of the air barrier movement. And when I was kind of trying to find some information on that, I came across an article in the Canadian Contractors magazine, and it was an interview with Harold Orr, and he was one of the lead engineers on the committee that pioneered the Saskatchewan Conservation House. And he was asked to reflect on the different stages of the development of energy efficient housing in Canada. And that's what he came up with. Stage one was to find a way to measure, that's okay, find a way to measure where the leakage of energy happens in a house. And what was written in the article, and that was news to me, so I'll share it with you, is that at the time, there was no efficient way of testing it for air leakage in a house. So the first thing that he came up with was to use tracer gases and trying to do that. And that was, the equipment and everything was quite expensive. And there was no way that that could be repeated on multiple houses. So at scale anyway. So he then came up with a methodology that was pretty much a plywood with a fan in it and some equipment to measure what was going through. So that was in the 70s. And yeah, like that testing hasn't changed tons, except the equipment got a little bit better. But it's amazing to think that the blower door test came out of this kind of early evolution. The second stage was to find a way to minimize the waste of energy. And I talked a little bit about that in terms of using an air barrier as an element, a critical barrier in your wall and roof and envelope in general. And the third stage was going out and teaching others how to build it. So it's one thing to do it for one house, but it's another thing to educate more than yourself, people to go ahead and be able to do those things. And then finally, developing software to design energy efficient homes, right? I think that what I wanted to take about that, those 4 stages, is a couple of things, like going out and teaching, making sure that what you were establishing was an acceptable level, and of course, having the tools to kind of verify all this, the equipment to test and the software to evaluate where you were going to be. So how important is air tightness? It's amazing that so many phones are not on silent. Anyhow, how important is it? it can be quite important. I think that in his article, he pointed to a 50% improvement when he introduced the concept of a well-designed and well-installed air barrier. And those numbers, which I took from a much more recent publication, kind of demonstrate that a little bit. You can see that if your baseline was at 0.4 CFM per square foot at 75 Pascal, that without an air barrier, like let's take the edge of the scale, there's like a 60% difference in the heating demand, right? Just like that's kind of like what we're now expecting of buildings, more or less, 0.4 CFM. Now, does that mean that we need to stop there? No, there's lots of opportunity still. But what I wanted to demonstrate here is really the scale at which the air barrier can make a difference. I also wanted to kind of like see what the air tightness over time has been, and that's a little bit harder to get the data. Again, nice presentation from RDH. I was able to kind of steal a few graphics in here. The 1900s to the 2000s, you can see the little dip towards the end when air barriers became a thing. Like that's kind of going back testing, right? And the information that is in the middle graph is kind of like showing that we're also improving over time within the context of where we are now standing, right? And you can see that at the end, kind of how distributed the data is, like how different the worst to the best performer is. It's like tightening. That's kind of like, you can see the funnel is kind of closing in. And that's because those data points mostly were buildings that needed to meet a certain standard and knew they would be tested. Whereas the data points of the graph that are before that have more to do with buildings that were voluntarily meeting a certain standard or were kind of tested because they were looked at in the context of a retrofit and data was accumulated, right? So you can see already that difference. And if we look at the impact of mandatory testing, kind of like between different types of building, the graph from RDH kind of like included those research projects, the US Army Corps projects that were tested, and in Seattle, because that came earlier, so there was data points for that graph on that. And you can see in this graph, it kind of shows what I was saying in a previous slide, right? Like, not only the mean did go down, but also the data was also much narrower in its result. So that brings another question. If you're not testing, are you really getting what you're expecting, right? I think that we've established with the leaky condo that having something in the code that tells you you need to do something is very important. We can also put energy and energy standards in there, and right now we have kind of testing for air leakage, but I'm wondering, is the next thing that needs to be really tested through measurement and verification is the actual performance of the building? If we are now pushing so hard on energy modeling and meeting a certain target, should we not make sure we're actually meeting exactly what we want? Not through just research because we're interested and we do that little pocket, but by reporting. So that is kind of like the part of my presentation that's kind of the past. So I thought I would like kind of summarize a few points. Of all those stories, patience is in order. Changes take time. It doesn't happen over a year, over two, it happens over decades mostly. Ideology is great and critical. Like having a lofty goal is essential to getting to the right place. But for long-lasting implementation, the code and the legislation needs to actually support that and kind of reinforce it. While legislation goes a long way, like charting the path ahead and giving the people the tools they need, even having a demonstration project in there is really important too. And like I said, measurement and verification is key to obtaining what you need, what you want, and what you targeted. So it should be part of the equation too. And finally, history has a tendency to repeat itself. So let's not. Let's remind ourselves and be on guard for it not to happen again. So present day. I think we talked a lot about that. I'm very glad because I don't have to do a brief on embodied carbon. It was very well done, and there was a lot of the takeaways I wanted to give today that were given this morning, very fresh in memory, so I won't have to rehash them too much. But what I wanted to kind of counterbalance with that is that the two things that I think are very at play today is not only that we want to do something better for the environment, is that there's an economic crisis in terms of affordability for people. And I don't know, like, do we want to build a world in which nobody can afford to live in? Or do we want to try to achieve both, right? And we need to keep that in mind. So again, building envelope, not mechanical. So I'm not going to talk about that. Not embodied carbon so much as in the context of the balance of things. But, and again, non-combustible construction, so still stud, where thermal bridging really matters. So you have all this coming at you, all the changes of code and all that kind of stuff, and you want to do the right thing for the environment, and all of a sudden, like, all the questions are coming. You're sitting in a meeting and people are asking, and like, what is it that I need to do for this? And like, how do I meet that? And if I do that, is that better than this? And like, it depends, right? At the end of the day, everybody's asking, can you just tell me what I need to do? Like, that's what I get in most of the meetings after we discuss too much, because they don't have the background to make necessarily the decisions. When we talk about developers, the guys with the money, the people with the money in developing those projects. So, yeah, like, how do we go about doing that? Even myself, I'm listening to all the presentations here this week, right? And there's a lot of information. Sometimes it makes my head spin, because between like being paralyzed by what I'm hearing and not knowing what to do and wanting to do the right things, like, where do you start, right? So I thought I would like kind of try to bring it back to what I do and give you a few things that could be kind of a good reminder for some and a good takeaway for others. Again, I don't need to go over that, except perhaps in the context that I'm from British Columbia, right? You can see on this graph that the intensity of our grid is pretty low. So I'll tell you, when I'm in meetings and there's people that have tunnel vision, perhaps about embodied carbon, I get so much pressure about taking out the insulation because it doesn't matter on the emission that you wouldn't believe. So just putting that in context of what I'm going to tell you next. My rule number one is the best savings is what you don't use in the first place, right? So with an energy performance goal in mind, either dictated by code or by a sustainability goal or a code, starting to make think about beneficial decisions that would make reduction in the amount of material you need to get to a certain thermal performance. So again, what you have to understand is that I work in the context of not, I would say 90% of the building I do, they're code buildings. They're not like, they're maybe 2% better than code, not 50% better than code. So the environment in which I work is trying to make the most of my sandbox, right? So what about the perfect wall? As wall, like, again, think about Vancouver. We're building to the property line. We're having issues with wall thickness. So should we start really considering heavily using hybrid walls on every project? Well, we have vapor permeable membrane, we have intelligent vapor barrier, and there's limitation also to cladding attachment, right? Like there's so much you can put on the outside with the wind loads and everything. So don't make stupid decisions for the wrong reason. And I'm gonna try to demonstrate how I approach this, try to avoid building walls that are not suited for where they're used. Of course, when you're talking about affecting the TEDI, the thermal energy demand intensity, like you can look at affecting the air tightness. We looked at the graph, you can make a difference with that, right? So I've talked about that, I won't come back on it. And heat recovery, same thing. The TEDI, the heat recovery makes a big difference in the TEDI, like the efficiency of it. So you can make a difference just by changing the efficiency of your equipment. That's pretty straightforward, so won't touch that more than this. And the window wall ratio is also something that you need to think about, right? Like, that's what you mentioned earlier, right? Form matters. In what we do, like the form matters so much that it dwarfs everything else. In this, what I wanted to kind of show with that data is that if you take a building, of course, in high rises, we're losing heat through the wall mostly, right? Like the roof is like a tiny part. The walls of a tall building are a big surface area of heat loss. So the way that this is presented is by vertical surface area compared to floor area. And when you have a VFAR, we call it, of about 0.5, like for the square at 600 meter, you get about a TEDI, forget the unit, I just want to talk about proportion. So you get about 30, a TEDI of 30, that's in kilowatt hour meter square. If on the opposite end of the spectrum, you were to do a single loaded corridor, U-shaped building because the courtyard is quite nice, then you would be closer to 60. That's 15 TEDI. That's like 50% difference just with the form. Another tool that's pretty cool is Building Pathfinder. What I wanted to do is go one step further than telling you that it's important. I want to show you how for the same other data, like window ratio, wall R value, roof, like everything stays the same. This is the difference it makes between having a typical narrow or complex form. Like you can see the results. And that's why that's a super cool tool, because it visualizes like the results as you go. On the other side, if you were to say, okay, I really want that courtyard, what kind of wall do I need to get there? What kind of difference do you think walls will make over the teddy? So I chose the complex, which is the middle one, right? Like it was not the narrow one-sided corridor. It was the one in the middle. So it was the 45. And that's how much difference. I'm playing between R16 and R30 overall, considering all the thermal bridging. That's how much difference I'm making with the wall. So if you want to know if form is important, and that doesn't convince you, I don't know what will. So at the end of the day, not all buildings need to be iconic. Something simple can do the trick. Yeah. Okay. So on that note, I'll leave you with 3 things, and I'll go very fast. I'm just gonna say a few things. Is that because the linear transmittance is important and the length and the window, think about how you're installing your window. It makes a huge difference. That is also something that you can do to reduce the amount of insulation you need to get to a spot. The form of your window makes a difference. Like 2-punch window, 1-punch window, same area, like 40% of your wall, it makes a difference. So think about that. The balcony form makes a difference, let alone that the inset balcony also changes your form. Like how you can deal with it with its attachment makes a difference. Best thing is probably no balcony, but livability comes into play in high rises. So, and then I will leave you on this with this is that I didn't go too much in carbon, but this is a study that was done in BC for that is more enclosure centric. So if you want to go and dig into that, I invite you to do so.
Awesome, awesome, awesome. Got a lot of people that are needing to travel with shuttles and everything else. You get to ask the one and only question.
Oh my goodness, such pressure. So my question is about the leaky condo crisis. So you had, that was something I am not very familiar with. You had a lot of interesting kind of potential factors that could have caused or amplified that. I didn't see on that list anything that was like specifically or uniquely residential versus commercial. So my question is, why was it condos that had the crisis versus all other buildings that were being built at that same time?
The wood frame condos experienced the worst damage. There are condos that were high rises, steel stud. They came a little bit later. The deterioration for those, the mechanism by which kind of like it's to a point that you need to do something, like took more time. And the institutional, perhaps like people engaged on those projects were also a little bit more knowledgeable. There are some, we've repaired schools and we've repaired that face the same thing, but the failures were not as big at that level.
Okay.
So I think that the wood frame and commodity kind of construction, that's what experienced the biggest impact.
And was that not allowed in the commercial code? Was it a difference between the residential and
No, there was no difference.
Okay, no difference.
No.
Okay, thanks.
Well, with that, thank you, phenomenal.